Good afternoon, and welcome to this session of Bioproducts and Biorefinery within the framework of Tecnicelpa. In this session, 3 papers will be presented. For each paper, we have 20 minutes for the presentation, and at the end, with everyone, we will have 5 minutes for Q&A. Let us begin with the first paper. First paper is Eucalyptus leaves extracts rich in triterpenic acids, presented by Pedro Branco. Pedro Branco holds a degree in technological chemistry, a master's in applied analytical chemistry from the University of Lisbon, and a PhD in organic chemistry from the University of Madeira. He has over 20 years of experience in natural products chemistry and lignocellulosic materials. Since joining REIS in 2016, he has led technical project management in bioproducts, biomaterials, waste valorization, and circular economy. He has supervised students across academic levels and is co-author of more than 20 scientific publications. He has been an invited speaker at over 10 national and international conferences and seminars, and Pedro is also co-inventor of 3 granted patents and 2 other under evaluation. Pedro, let's welcome Pedro. And Pedro, the floor is yours. You can start.
Good afternoon, everyone. Today I will be presenting our work on eucalyptus leaf extracts rich in triterpenic acids. This study is part of a collaborative effort between REIS, the Forests and Paper Research Institute, what has happened here? The Collaborative Laboratory for Biorefineries and the University of Aveiro. The work is focused on developing green and circular processes for the recovery of bioactive compounds from eucalyptus residual biomass. So, putting this into context, the Portuguese pulp and paper industry heavily relies on eucalyptus wood, and during harvesting of the trees, hundreds of thousands of tons of residual biomass are generated every year. This includes, for example, leaves, barks, or small branches, which are often left in the fields or burned for energy purposes. And this represents a missed opportunity for resource optimization. These eucalyptus residues are a rich source of bioactive compounds such as essential oils, triterpenic acids, or phenolic compounds, and they have several therapeutic properties that makes them valuable for applications in various sectors, such as cosmetics, food and feed, nutraceutics, pharmaceutics, or even in perfumery. This shows that there is a whole unused value in eucalyptus residual biomass, and we need to adopt industrial sustainable bioactive compound recovery strategies for their valorization. Building on this potential, a recent patent developed by REIS, University of Aveiro, and University of Coimbra proposes an integrated process for the recovery of bioactive compounds from eucalyptus leaves. This process is a sequential extraction of several fractions. First, the essential oils, followed by the triterpenic acids, and finally, the phenolic compounds. A particularly innovative feature of this process is that it uses the essential oil itself as a bio-based solvent to extract the triterpenic acids. This approach offers several advantages as it enhances the resource efficiency by recovering the three main groups of bioactives in the eucalyptus leaves, and also it reduces the reliance on external organic solvents, thereby lowering the process costs and environmental impacts. Altogether, this represents a sustainable strategy that maximizes product value and it minimizes waste generation. However, after recovering the bioactive compounds, the residual biomass can still be used for energy generation, enabling the direct integration of this process in the current pulp and paper value stream in a biorefinery perspective. Despite this potential, some barriers are slowing its industrial adoption, particularly the process optimization and the separation and purification challenges. The experimental procedure of this work, we defined it as first the extraction of the essential oils from the leaves, then the tritipenics were extracted using the essential oil as said before. We applied a box bank and statistical design to evaluate the effect of three variables: the extraction time, the temperature, and the solid to liquid ratio on three dependent responses: the triterpenic acids extraction yield and productivity, and their concentration in the extract. Then, the process was scaled up to the pilot level using forestry byproducts composed of leaves and small branches, which are representative of the industrial residual biomass. In this step, we also introduced ethanol as a conventional used solvent as a comparison. Finally, the preparative absorption chromatography was used with macroporous polymeric resin for isolating the triterpenic acids. In this way, we aim to develop a sustainable and extraction method for recovering the triterpenic acids from the eucalyptus globulus leaves using the essential oil as a solvent. Going for the optimization studies, this was the first part where we found that high temperature, high solid to liquid ratio, and minimum extraction time to be the optimal conditions, predicting a maximum yield close of 20 grams of triterpenic acids per kilogram of dry biomass. These conditions offered the best compromise between yield and processing time, maximizing productivity, being industrial advantages by reducing extraction duration up to 8-fold while maintaining high recovery when compared to the maximum yield that we can obtain. When we validated these results at the pilot scale, this process maintained the similar results, confirming that the extraction process that we defined is scalable and robust. When compared to the extraction with ethanol, we found that altogether it achieved similar yields as with essential oil, but it had a much higher concentration of the triterpenic acids, around 160 milligrams per gram of extract after solvent evaporation, when compared to the 3 milligrams per gram of the extract in essential oil. Because in this case, we could not evaporate the solvent and therefore concentrate the extracts. This highlights that the main limitation for using essential oil is that we cannot recover the triterpenic acids from the solvent, although it's a really sustainable alternative. So the major challenge still is that we have to find strategies to purify that to be commercially viable. We then used, as I said, the chromatography with the adsorption chromatography to try to enrich these eucalyptus extracts. He used a moderately hydrophobic macroporous resin, and the two types of extracts, the extract in essential oil and the extract obtained from ethanol, with this technique. For the essential oil extract, the breakthrough curve shows that there is no preference for the tritipenic acids and the essential oil. Both compete for the adsorption sites. This indicates that this technique is limited to purify the essential oil extract. In contrast, the ethanol extract exhibited that the resin is selective for tritipenic acids, while polar compounds such as sugars, phenolic acids, or inositol are eluted early in the process. This shows that future optimization should include prior recovery of the essential oil before the adsorption chromatography. Also, for the elution curves, it can be seen that there is no preferential adsorption of the tritipenic acids, as they elute firstly in the early fractions, as you can see in the left of the graph in the top. However, in the dilution of the ethanol extract, it can be seen that we can concentrate and elute the triterpenic acids only in several fractions, and these two fractions particularly, they reveal that 60% increase in the concentration of the triterpenic acids can be achieved, confirming that this chromatography can effectively enrich these bioactive extracts. Moreover, the purified fractions below, these images below, are lighter in color, indicating that the pigments were removed, mainly chlorophylls. Further optimization of the polarity of eluents, flow rate and volume is still possible and required to maximize the recovery and selectivity. So, as a conclusion and the future work, our work highlights the potential of sustainable and integrated approach for the recovery of tritipenic acids from Eucalyptus globulus leaves, and we optimize the extraction conditions at the laboratory scale that maximize tritipenic acids recovery while using the essential oil as a bio-based solvent while minimizing the processing time. There is an excellent agreement between laboratory and pilot scales, demonstrating the scalability and robustness of this process. Based on the conventionally obtained tritipenic acids extract, that is, with ethanol, adsorption chromatography proved to be a promising technique for the extraction for the enrichment of tritipenic acids and clarification, but to the essential oils extract, future studies must focus on prior recovery of the essential oil, for example, using distillation methods, and the optimization of the elution conditions to further enhance the efficiency and the selectivity of processes. These are significant advances for promoting the future integration of high-value valorization strategies for eucalyptus residues, and ultimately this research contributes to advancing the circular valorization of eucalyptus residues, paving the way for the recovery of high-value bioactive compounds with significant market reports. Thank you very much for your attention.
Pedro, thank you for your presentation. 10 minutes, it means we have 10 minutes for other. Now we will go for the second. And for the second work, we have From Waste to Resource, Harnessing Pinecone-Derived Lignin for Sustainable Chromium-6 Adsorption, presented by Ricardo Costa. Ricardo Costa is a PhD student of Forestry and Natural Resources from Centro de Estudos Florestais at Instituto Superior de Agronomia. He took the bachelor and the master's degrees in Forestry Engineering and Natural Resources in same university. He works with valorization of lignocellulosic materials and is developing his work in lignin extraction and nanoparticles production for value-added products. The floor is yours.
So, hello everyone. Thank you for the kind introduction and the acceptance for me to present my work. So my work, I'm a PhD student and I am trying to valorize residues from the pine nut industry, and this presentation will focus on the valorization of lignin of pine cones and its ability to absorb chromium-6 from water. And beginning from an introduction about the pine nut industry, so Pinus pinea or stone pine is the 5th most planted tree species in Portugal, and it's mainly used for its fruit, in this case nuts, that is widely used in the food industry, especially around winter and Christmas time, and associated with the exploitation of this fruit, there's the generation of byproducts, in this case pine cones and nutshells, which in the industry are basically densified and burned to produce energy, and these byproducts have a huge valorization. So as you see, for each harvested pine cone, so 57% of its fresh weight, it's the cone itself, 10% the nutshells, and only 3% are the nuts, and the rest is moisture content. In this work, so in my work, I worked with both byproducts, but in this presentation, I will only focus on pine cones. And so here we have the chemical composition of this pine cone. So we see a minimal content of ashes and 6% of extractives. These extractives are mainly soluble in polar solvents and very rich in limonene, for example. And we see that it's highly enriched in lignin with 36%, and the rest 57% of polysaccharides, so hemicellulose and cellulose. So it has a lot of lignin that we can extract and valorize. And changing the subject to chromium-6, so chromium-6 pollution by industries has been increasing, and chromium-6 is highly toxic, carcinogenic, highly soluble and mobile in groundwater, and is easily absorbed by living organisms. And on the right we have some examples of industries that release chromium in its effluents, and chromium can exist in two states, so chromium-6, which is very harmful, and chromium-3, which is less toxic, less mobile in water, and insoluble because it forms complexes. There are many technologies for removing chromium-6 from water, as you can see on the left, but they have hindrances, cost-related, feasibility, maintenance, monitoring, and some technologies produce a sludge that it's very hard and it's harmful to get rid of. And so there's where it comes adsorption, in this case adsorption with lignin. So it's a more friendly way of removing chromium from water. So we just basically mix lignin with water that has chromium, and the chromium will be absorbed by the lignin. Of course, there's also some hindrances in using by adsorption. For example, water will have many ions, so not only chromium, and so there will be competition of ions in being absorbed by the lignin. And so how does it work, this absorption between chromium and lignin? So in acidic conditions, chromium we did solutions of potassium dichromate, and in acidic conditions it exists in the form of dichromate and hydrogen chromate, which are negatively charged, and lignin will be positively charged, so there will be an attraction between chromium and the surface of the lignin. And then lignin will donate electrons, and those electrons will reduce chromium-6 to chromium-3, which is the reduction step. And finally, there will be a complexation phase step where the chromium-3 ions will form bonds with oxygen atoms from lignin, so chromium-oxygen complexes. And so basically the objective was to assess the lignin, our lignin from pine cones in absorbing chromium-6 from water, so to assess its capacity. So we did two types of extraction, so craft extraction, craft lignin, and an organosolv extraction. Craft extraction was used with more harsh conditions than normal pulp used in the craft process. So pine cones, lignin from pine cones is mainly as units H and G lignin units, so it's a more condensed lignin structure, so it needs harsher conditions to remove the lignin. And then we used the organosolv extraction with ethanol and water and catalyzed with chlorhydric acid, so to attack sugars and enhance the lignin extraction. And it's a more friendly environment extraction process of lignin. Here you have the images of the extraction, in this case from the organosolv extraction. So first image, we have lignin solubilized in the ethanolic fractions. Then we precipitated dropwise in water, the second image. And then we separated the lignin from the water. And by the end, we lyophilized to obtain our lignin powder. For the craft extraction, we basically dropped the pH with sulfuric acid to 2. We precipitated the lignin, and then we separated the precipitated lignin from the water in the same way as the organosolv extraction. Then we did chromium adsorption with the lignin, so we prepared chromium-6 solutions with potassium dichromate. pH was adjusted to 2 because we did previous studies with pHs between 1 and 6 and found that at pH 2 we had more adsorptions of the chromium into lignin, and we did a loading of 1 gram of lignin per liter of solution, in this case 100 milligrams per 100 milliliters of solution. In the first image we have a shaker with the lignin and the chromium solutions, and then the second we filtrated the lignin from the adsorbed solutions, and then we quantified chromium-6 solution after adsorption with the 1,5-diphenylcarbazine method. So this compound reacts with chromium-6 present in the solution and changes color to a pink brown color. This is more a brown color because this solution had a lot of chromium, but in our calibration curve, so we used only chromium concentration between 0 and 1.5 milligrams per liter of chromium per liter, and the color of the solution was pinkish. So we did this by spectrophotometer at a wavelength of 540 nanometers. Then we analyzed the absorption by 2 methods. So we did absorption kinetics to measure the rate of the chromium absorption onto lignin. Here, in all our experiments, the chromium concentration was 50 milligrams of chromium per liter, and we did contact times between 10 minutes and 24 hours. And then we did adsorption isotherms to describe the relationship between chromium into the lignin and chromium that stays in the solution after the absorption. And in this case, we used chromium solutions between 10 milligrams of chromium per liter and 1,500 milligrams of chromium per liter. And the contact time was based on the best results for each lignin on the adsorption kinetics. So passing into the results, so on the left we have an image of a chromium solution. This one had 100 milligrams of chromium per liter, and the right image is after absorption, where almost all the chromium was removed, and the light color is basically of the product of lignin, a little bit of lignin solubilization. So after we have the results here from the adsorption kinetics, so in red we have the Kraft lignin, and in blue the organosolv lignin. We can see that Kraft lignin had a faster adsorption rate than organosolv lignin, and after 3 hours it had absorbed all the lignin present in all the chromium present in the solution. Organosolv lignin, on the other hand, needed 6 hours to absorb all the chromium in the solution. We adjusted models, adsorption kinetic models, and found that the pseudo-second order model displayed the best fit for both lignins, which makes sense because this model basically says that the rate limiting step of our experiments it's basically between chemical interactions between chromium and lignin, in this case the reduction of chromium 6 to chromium 3. And so after these results, we did our adsorption isotherms. And so for Kraft lignin, we did 3 hours of adsorption. And for organosolv lignin, we did 6 hours, which were the times that best fit for the maximum lignin adsorption at a concentration of chromium of 50 milligrams per liter of solution. And so here we have results, and we see that we have a huge difference on both lignins. So in the case of Kraft lignin, after 3 hours, so in the X we have the chromium that was left in the liquids, and in the Y we have the chromium, milligrams of chromium that was adsorbed onto the lignin. So we saw that after 3 hours, Kraft lignin had a maximum absorption capacity of 340 milligrams of chromium per gram of lignin. Organosolv lignin, on the other hand, after 6 hours, so double the time of the Kraft lignin, displayed only 162 milligrams of chromium adsorbed per gram of lignin, so half of the Kraft lignin. We did experiments with more time for the organosolv lignin just to see if with more time we could achieve more chromium absorption, and we found out that with 24 hours we could reach the 350 milligrams of chromium adsorbed into the organosolv lignin. So, but it's a huge difference. After 3 hours, Kraft lignin displayed a huge absorption of chromium. So we also fitted models for the adsorption isotherms, in this case the Kraft lignin. We found that the Temkin model was the best fit for the Kraft lignin, which accounts for as the chromium is being adsorbed by the lignin, less sites are available for the chromium to be reduced and attached to the lignin. On the other hand, organosolv lignin, with the organosolv lignin, the languid model provided the best fit. Temkin also was a good fit with 0.96, but Langmuir was the best fit, which assumed a monolayer, so the chromium particles are adsorbed into the lignin in a monolayer fashion. So then we also characterize the lignin by SEM. So we have the Kraft lignin on top on the left before absorption, on the right after absorption, organosolv lignin on the bottom. We didn't see many differences in the lignin surface before absorption and after absorption. We can see that Kraft lignin has both spheric particles and irregular particles, and maybe it's hard to see, but it has also very small particles. On the other hand, organosolv lignin was the size was more homogeneous, and all the particles were very irregular. And also difficult to see in the kraft lignin, we have some presence of pores, and in organosolv lignin no, which can also explain why kraft lignin had very good results in absorbing chromium. We also did FTIR after and before adsorptions. So in red after chromium absorption, black original lignin. Both FTIR were normalized at 1030, and there's so difference in the chemical structure, functional groups of lignin. But I will not get very long with this. But we can see that between 900 and 400, we have the emergence of new peaks. Based on literature, we can see that it is associated with chromium lignin complexes, and overall the majority of bands increased after adsorption. Here it's kraft lignin, and on this graph is organosolv lignin, which follows the same profile. There's a difference. For example, here in the organosolv lignin, we see that at 1268 and 1200 there's an increase in the absorbance after chromium adsorption. And for example, in kraft lignin there is no difference, so it's the same. And with kraft lignin there's an increase at 1130, and for kraft lignin, and in organosolv lignin there was no difference. So there are differences in the chemical structure, functional groups of the different lignins. And finally, we also did analytical pyrolysis to assess the H and G units of the lignin structures. We can see in red compounds that increased after adsorptions, in green compounds that increased after adsorption, and in red compounds that decreased after adsorptions. We can see some differences in the original lignin of kraft and organosolv. For example, kraft lignin is more rich in guaiacol units, while organosolv lignin is more rich in 4-methyl guaiacol, which makes sense because so in kraft extraction we use harsher treatments, which will break the beta-4 linkages, and in organosolv it's less harsh, so we will have less condensed lignin structure, and those beta-4 linkages are not destroyed, broken. But we can see a difference in, so after absorption we have more phenolic compounds. And so to finalize, we can see that lignin from pine cones, not only from pine cones, all the lignin can be used to adsorb chromium. In this case, lignin from pine cones from Pinus pinea. We also did on nutshells, and we had also very good results. We can also, a way that we can go, for example, is try to functionalize lignin to see if we can have better results at chromium adsorption, so higher chromium adsorption by gram of lignin, and all the biomass can be used to adsorb metal ions. Even we did experiments, for example, with grinded pine cone. We had chromium adsorbed, but way less. So, for example, only 20 milligrams of chromium was adsorbed per gram of grinded pine cones. So in this we can do biorefinery potential. So we have our pine cones, we can extract with solvents to valorize the extractives. We can, for example, do a thermal treatment to remove hemicelluloses and produce bioethanol, and then we can then go to the lignin extractions, valorize that lignin extraction, in this case with chromium adsorption, and we'll have then a fraction more rich in cellulose, which can be valorized in another way. So lastly, I want to thank you to everyone that participated in this work, and the FCT, which is the main financial institute. And thank you for listening.
Ricardo, thank you for your presentation. Just on time. For the third and last work, we have the biorefining Norway SPRUCE-BASED bioresources with the green solvent γ-VALEROLACTONE, presented by Carlos Medina.
Thank you very much, Mr. Chairman. Good afternoon, everyone.
Carlos, I will
Carlos
introduce
Martín. I'm coming from the... Yeah.
Just a moment, I will introduce you.
Oh, verlot.
Carlos Medina is a professor of biomass and bioresources at University of Inland Norway and a visiting professor at Umeå University. His research focuses on wood chemistry, linocellulosic biorefineries, biofuels, and biopolymers. Carlos holds a Master Science from the Leningrad Forest Technical Academy, a PhD from the University of Matanzas and Lund University, and conducted postdoctoral research at the RISO, DTU, National Laboratory in Denmark, and Costa University in Sweden. He also worked at the Tunen Institute of Food Research as an Humboldt Foundation Fellow. Carlos, the floor is yours. You can start.
Thank you very much, Mr. Chairman. Good afternoon, everyone. Yes, I'm Carlos Martín, and today I will speak about our results on using γ-VALEROLACTONE, GVL, for pre-treating Norway spruce. And I'm representing here a large group of researchers from 4 institutions in Norway and Sweden. Some of them are sitting down there. The University of Inland Norway is the youngest university in Norway. It's a multi-campus institution with several campuses in the inland county in Norway, which, by the way, is the only county in Norway with no fjords. And we are sitting in Hamar, in the Department of Biotechnology, and Hamar, as you can see in the map, is quite close to Oslo, and you are all welcome there whenever you wish it. And this is the outline of my presentation, and I will start with a brief introduction about biorefining. We all know that biorefining is the sustainable processing of biomass into many different valuable products, and that this is something crucial for the transition to a circular bioeconomy. It's for a sustainable biorefinery, it's very important to use local resources. And in the Nordic scenario, Norway spruce is a relevant local feedstock because it represents up to 40% of the standing stock in Nordic forests. However, as softwood, Norway spruce is quite recalcitrant. That's why pretreatment is required, and it can be performed by organosolve using organic solvents that solubilize lignin and hemicelluloses and activate cellulose to enzymatic saccharification. And green solvents are a good alternative for organosolve, and one of them is γ-VALEROLACTONE, GVL, which has proven to be efficient for hardwood and also for agricultural residues. However, when we started this study 5 years ago, there were no reports on using it in softwood. That's why our goal was to explore its potential for biorefining Norway spruce using 3 different scenarios. The first one is using sawdust for pretreatment. The second one is recovering lignin from hydrolysis lignin, the residue of enzymatic saccharification. And the third one is recovering lignin from steam exploded pulp from a plant producing wood sugars and pellets. And yeah, here we have the three materials that we work with. We treated all of them with a GVL mixed with water. In some cases, we added sulfuric acid. In other cases, we added ethanol. And we started with sawdust. And here we varied the GVL to water ratio, different proportions, and we kept constant all the other variables. In this initial investigation, we saw that GVL was quite effective in solubilizing lignin and hemicelluloses, and that the solubilization of hemicelluloses increased with the decrease of the GVL to water ratio. The lignin also did, but it reached a maximum at a ratio of 40 to 60. And the hemicellulose solubilization trend was confirmed by the sugar concentrations in the liquors. After this, we varied the temperature and time and kept the other parameters constant. And we got pulps enriched in cellulose. And as we can see in the left figure, with increase of the severity of the treatment, we get pulps richer in cellulose and with lower content of hemicelluloses and lignin. And then using mass balances, we could get numbers on the solubilization of hemicelluloses, lignin, and on the recovery of cellulose. The solid state NMR confirmed the lignin solubilization and its dependence on the extraction temperature. Then we analyzed also the sugars in the pre-treatment liquors, and you can see in the left top graph that the sugar concentration, the sum of all the sugars, increased with the severity until reaching a certain point, and then it decreased. And then if we look here, this is the hemicellulosic sugars. They reach a maximum at about 185 degrees and 45 minutes, and then went down. And the glucose up here increased continuously with the severity of the treatment. And here are the degradation products that they increased continuously, and that's the reason why the sugars there decreased after 190 degrees. The enzymatic saccharification of cellulose was much better for all the pretreated pulps than for the raw material. It's the small one there to the left. And you can see that the enzymatic conversion increased with the severity, but only until reaching certain point. And we could identify optimal conditions for cellulose conversion at around 205 degrees, and I think it was 45 degrees, something like that. Minutes, sorry. Then we precipitated the lignin from the liquors by anti-solvent precipitation. We regenerated it, and the regenerated lignins were characterized by several techniques. The FTIR and the pyrolysis GCMS, both together, showed the lignin nature of the isolates. And it also showed that there was slow amount of pseudolignin contained in the regenerated lignins. The liquid state NMR showed that within the temperature increase resulted in changes in the proportions of the lignin interunit linkages. And with this, we established a biorefinery concept where we reached an effective fractionation of the biomass with a high a high enzymatic conversion of cellulose, and with regenerating of lignins of high quality. Up to this point, everything was done in the lab scale. But then we validated this at pilot scale using a 50-liter reactor. And we also ran the enzymatic saccharification in rather pilot scale conditions. And we ran hydrothermal liquefaction of the lignins, both the regenerated lignin and also the hydrolysis lignin, the residue of the enzymatic saccharification. We also did, even if it was not at pilot scale, the fermentation of the cellulosic hydrolysates to ethanol. It fermented with high yields. And the dehydration of the hemicellulosic sugars to furan aldehydes. We were not that lucky with that final action, but yeah, it's something to come back to it. After this, we worked with hydrolysis lignin from the demo biorefinery plant in North Sweden. And the hydrolysis lignin usually it's more or less 50-50 cellulose lignin, but it can contain also some hemicellulose residues and also some ash and other minor components. And if one wants to valorize this material to high added value applications, one needs to isolate the lignin from the other constituents. And we thought that we could do that using GVL. Yeah, we tried it, and we used here two systems. It was in both cases GVL with water at the 80-20 ratio, but in one of the cases was acid-free, and in the other one it was assisted by small amounts of sulfuric acid. We get we get rather good lignin solubilization with the acid-free system, and the solubilization increased with the temperature and the time. And we also get quite high cellulose recovery in the residues. Then, with the acid-assisted system, we get higher lignin solubilization, but we got a sharp decrease on the cellulose recovery. That's not that good. Then here again, we regenerated the lignins and characterized them. The chemical composition showed that the regenerated lignins had about 90% lignin content, about 5 or 6 content of polysaccharides, and while the pseudo-lignin content was below 10%. And if we compare that with the extraction residues, we see that it's exactly the opposite. It's completely exhausted. Then by FTIR, we couldn't find major differences between the lignin extracted with the two systems, except for that peak over there, that we think that it can be attributed to pseudolignin, and it was seen only in the lignin from the sulfuric acid assisted system. Then this was confirmed by the solid state NMR, where we see strong lignin related signals in both lignins. And if we compare this with the extraction residue, we can see that the lignin-related signals are weaker, and instead we have strong carbohydrate-related signals. Okay, until this point, both lignins showed similarities, but when we came to the molecular weight, then some interesting and slightly different trends were revealed. First, the molecular weight increased with the temperature, and it kept more or less constant with the liquid to solid ratio. That's for the acid-free systems. But the most interesting thing here is this. the polydispersity values of the lignins from the acid-free system was quite low, and with no apparent changes depending on the condition. What happened with the lignin from the acid-assisted extraction? Okay, here we see that there was a very sharp increase in the molecular weight, and also that the polydispersity values also increased enormously, especially above 190 degrees. So here the polydispersity values indicate that we got two rather different lignins. One of them is very homogeneous, the other one is rather heterogeneous. And this can anticipate different properties for these two lignins and consequently different applications. Then we did also the liquid state NMR of the regenerated lignins. We saw lignin-related signals, all of them, but the interesting thing was this. The signal of the phenylcoumarine structures were stronger than those of the beta-O4 linkages, and that was for both lignins. And this is an indication of structural changes happening during processing with the formation of new carbon-carbon linkages. This study is published. You can find details here. And finally, we extracted lignin from steam exploded pulp. And we used here first different temperatures and time, and we see that the lignin solubilization increased with the temperature and time. Then we tested, instead of the binary GVL water system, we tried a ternary system where we added ethanol. And we tested 4 different ratios. 5, sorry. And we got that as the GVL share in the ternary system decreases, the lignin solubilization also decreased. But the lignin regeneration from the liquor increased. And here again, these are the two lignins, one where we had ethanol, the other one with GVL, and then we did the chemical composition with wet chemistry and also with pyrolysis GCMS. You can see there the results. And then with the size exclusion chromatography, we compared the molecular weight distribution, which was quite close. The only difference is the peak down there that was visible in all the GVL samples, and that one can perhaps attribute it to pseudolignin. Then the liquid state NMR revealed that the beta-O4 linkages in lignin were better preserved after the GVL pretreatment than after ethanol pretreatment. And the FTIR also confirmed similarities between the two lignins, except some peaks attributable to pseudo-lignin that were only in the GVL lignin. And with this we come to some final remarks or conclusions. GVL proved to be effective for treating different Norway spruce biomasses. And we also found that adding a small amount of sulfuric acid to the GVL water mixture improves the yields. But when we do acid-free GVL treatment, we get lignins of higher purity. Also, when adding ethanol, we found that adding ethanol reduces the pseudolignin content, But on the other side, on the other hand, the ethanol-free treatment produced lignins with a better preservation of the beta-O4 linkages. And I think that all of these support the use of GVL in integrated softwood biorefineries. And before finishing, I just inform about this. I'm here representing the Nordic Pulp and Paper Research Journal, which is a journal publishing results on pulp and paper research, also on biorefinery and bioproducts. I would like to encourage all of you to submit papers to this journal. I think that this scenario here could benefit all that we are discussing here could be spread further by publication in this journal that is highly specialized. And finally, I want to thank the funding organizations that supported this, the Swedish Energy Agency, Kempe Foundations, Bio for Energy, and the institutions participating here. And of course, thank you very much for your attention. And sorry that I went further. Yeah. Anyway, I'm open for questions.
So after these three great presentations, we can start the Q&A session, and we have 10 minutes for that. We'll start.
Yeah, hello. My name is Christian Biermann from Chimera Chemicals. I have a question on the first presentation. Do you plan to use some solvents like supercritical carbon dioxide, for instance, as extractive? Or also
I'm not hearing here.
Pardon?
Can you please repeat?
Okay, of course.
Understand.
Of course. Yeah, I found it very interesting, and I was asking if you were also thinking about using supercritical carbon dioxide to extract the content of the eucalyptus leaves.
So for this particular class of compounds, we have also running in parallel some extraction methods with supercritical CO2 doing that. But this work is focused on having greener solvents other than the traditional ones, but having solid liquid extractions, traditional, but with alternative solvents.
Thank you very much.
Thank you for your nice presentation. Dmitry Evtugin from University of Aveiro. And my question to Pedro is, in your approach, you use just small fraction of the tree foliage biomass, okay? The rest of materials are becoming wastes. Do you think that comprehensive uses of tree foliage is not interesting approach, because actually you lose chlorophylls, waxes, you lose carotenoids and another valuable compounds. Do you think that comprehensive utilization of other materials from tree foliage is an interesting approach?
Using other parts of the plant is what you mean, or?
In your approach, you have just small fraction of the compounds that you isolate for as a target product, yes? But the rest of the material, the rest of the tree foliage, your products may be less than 10% from tree foliage biomass, yes? So the rest of the material are vastus.
Waxes, yeah.
Yeah. So my question is, maybe the comprehensive approach is interesting in your case when you can use not only these three components that you isolate, but also chlorophyll, also waxes, also carotenoids. Oxalic acids, by the way, also is a huge amount in the leaves. In this case, you can improve the attractiveness of and the profitness of this kind of technology.
So focusing on the whole valorization of the components in the leaves. Yes, that's the main objective further in the future to have the maximum valorization. In this case, we are focused on the main groups of components, and the main valorizable, so to say, in this at this point. We can then look for other classes of components, of course, but in this work we are just focusing on these three and getting more value and getting more knowledge from this process that we developed for these three classes. It's of course always the possibility of getting more and more value, but for this, at this moment, we are just looking for these three classes of compounds. Yeah.
More questions? No more questions. No more questions.
Hi, my name is Sarah. I'm from the University of Inland Norway. Can you hear us? I think, yeah. And my question is also to Pedro. I was very intrigued by your presentation and the work that you did. I thought it was very innovative. And you presented these, the challenges that you face with the essential oil. And I was wondering, do you have any thoughts on how one could proceed further?
How to, sorry?
Do you have any ideas or thoughts, on how to proceed further to solve that challenge that you met with the essential oil?
Yeah. As I told in the presentation, probably the main, the first step is to distill the essential oil, and almost in one step only to do some rectification of the essential oil. The essential oil, the eucalyptus essential oil, normally is valorized after rectification, so enhancing the cineol content of the essential oil up to more than 80%. The crude essential oil that we used is about 60% cineol. So the first step is to distill and rectify the oil, and then the heavier fractions would contain the triterpenic acids, then to use still the chromatography as we use. So it's what we can do, the valorization of the essential oil and the triterpenic in one step, and then the purification of the triterpenics. That's probably one way to go for it. Yeah.
My question is to Ricardo, to the second presentation. In your presentation, you showed the amount of lignin in the pin cones. Is it formal classen lignin, or is it really pure lignin content?
Sorry, can you repeat? Is it
in the pine cone when you make the determination of the lignin content? I think 36%, something like this. Yeah. Was it formal classen lignin content, or it was true lignin content?
In this case, it's the class on lignin.
Well, in this case, you have a mixture between lignin and condensed tannins. When you make the isolation by Kraft method, you can recover a significant part of these tannins. When you make via organosolv lignin, not. So in this case, you have two different lignins. One is strongly contaminated with tannins, with free phenolic groups. And in the other approach, you have much less. So it's not question of lignin, it's question of contamination with the condensed tannins and their degradation products, you see? And the chromium chemistry is very complex with lignin. When you have chromium 6 and under acidic condition, yeah, in your case, the reaction is very quickly comes chromium 6 to chromium 3. In this case, your determination of chromium 6 is not valid anymore, and the type of the interaction of chromium with lignin are quite complex. It's not just simple chemisorption or sorption. It's also interaction PD stacking electrons. So I think that this point should be rethink, and some conclusion may be a little bit different from your work.
Okay, yeah. This work is still ongoing. So we also found that the extraction of lignin in the Kraft process, we can extract 50% of lignin. Of course, we have condensed tannins also. In the organosolv lignin, for example, we only achieved 15% of, so it's less, which is normal. Yeah.
I have two questions also. One for Ricardo. Ricardo, very interesting work to transform one waste to a resource. And considering the main differences between the softwood lignin and eucalyptus lignin, what can we expect, namely according to the content of syringeal groups in eucalyptus lignin? What can we expect in terms of performance when compared with the results of your study?
We actually also did a work with lignin from eucalyptus, and we found that, in this case Kraft lignin, we found that we needed 24 hours of adsorption. For example, in my work with the pine cones, we saw that Kraft lignin we only needed 3 hours to adsorb a quantity of 340 milligrams of chromium per gram of lignin. We found that with eucalyptus lignin we needed more time, so 24 hours, and we could reach more or less 300. So we had a little bit less of adsorbed chromium with more time of contact time.
Thank you. And to Carlos?
Yes.
To Carlos, I have one question. It's that after the wood to be fractionated, it's possible to recover the γ-lactone?
Thank you very much for the excellent question. I was just expecting it. Yeah, we actually need to recover γ-VALEROLACTONE, otherwise it will not be economically feasible, the process. How to do it, I don't know. But we, people in the academia, we can offer solutions. Then we have to see which of those solutions can be acceptable for the industry. We can think, for instance, if we do vacuum distillation, we distill evaporate water because GVL is very heavy. That could be one alternative, but it could be rather expensive. Another possibility could be salting out for having two phases with the GVL separated and then decantation. But again, the salts can be aggressive to the tubing and the system. Then we move to other alternatives. If we think about liquid extraction, using a hydrophobic solvent, let's say N-butane, then we get GVL solubilized in that solvent, and then we can separate that fraction from water, and then we can evaporate the solvent from GVL. Yeah, maybe it's feasible, I don't know. Still, we can move forward and try with carbon dioxide, either liquid carbon dioxide or supercritical carbon dioxide, or even better, with supercritical carbon dioxide with a co-solvent as enhancer, for instance, ethanol. I would believe that this last alternative could have some attractiveness for the industry, but I leave that on their side.
Yes, because this is very important to be this to apply this at the industrial scale.
Right. Yeah. Thank you.
Okay. So we are still closing this session. Please, let's thank